All right. So welcome everyone. This week we have Nilay Kundu from IIT Kanpur, who is going to tell us about Euclidean path integral optimization in CFTs. Nilay, thank you very much, and we'll be sure to interrupt with lots of questions.
Okay. So thanks. I would like to thank the group at Potsdam for giving me this opportunity. So it would have been great. I would like to visit at some point physically, but for me, this is like this way of giving a talk is the first time. But I hope it will go well. And so I will talk about this Euclidean path integral optimization in conformal field theories, and please feel free to stop me at any point if you have any questions or comments. So I'll try my best to come up with some arguments. Or so this will roughly be based on these three works. So I've been told that people would like to focus on the last one more in some more detail. But just to set it up, I will go through it a little slowly, a little quickly for the where I will cover the first two, where we generally proposed the idea and did some calculations supporting that proposal, and then the last one where we had Sumit Das and Arpan joining our previous collaboration to extend it to basically part out CFTs or things like that, which I will be roughly I will divide it in half and half. So the first half will mostly cover the basic setup, but a little quick. Please stop me if you need a little bit more explanation and things like that. So just to explain what I mean by my title of the talk. So there is a part where I'm saying it's an attempt to a better understanding of ADS safety, by which I mean we would like to kind of elevate its status from the conjecture, which we call it a conjecture, to a first principle understanding from that point of view. So this part is concerning that attitude. And then there is one ingredient which I'm calling Euclidean path integral for ground state wave functions in conformal field theories. I will explain it in more detail. And there's the element optimization, which is kind of connects these to this bigger goal and this Euclidean path integral approach through this optimization. And we kind of come up with also something as a byproduct, which is this recent interests in computational complexity and more importantly in the holographic context. So this will be related to this kind of tree diagram, if I may say so. Okay. Yeah, so I think I mean just to make it clear, we are considering it ADS CFT correspondence, which is kind of a statement of a duality between a quantum gravity in d plus 2 dimensions, for example, in anti-de Sitter spacetime, and it's related to conformal field theory on one lower dimension, the boundary, asymptotic boundary of this ADS space. And the duality works in various ways, at the level of symmetries, at the level of degrees of freedom, and more calculations by partition functions as a funnel of the boundary value. The gravity comes to the partition function of the field theory side. So I just to flash it. But even if we understand, I mean, people. So in some sense, this has become a kind of a paradigm, and so I mean, it came out as a byproduct of research in string theory. But people, for example, me, I mean, I started working in ADS safety correspondence, and this has by its own become a research direction. But still, till now, we just know it in terms of examples. I mean, obviously there are. I mean, no one doubts it, but it would be better to kind of understand it from more basic point of view. For example, if I'm given just some CFT data in the sense of operator content or whatever, can I do something just to see that, for example, the zeroth order question, to see the metric of anti-de-Sitter space coming out of that? So this attitude is to kind of try along that direction, but we will take a definite help from something which I will come to. So I mean, one important player in this game is obviously entanglement entropy, which kind of which is in a sense a measure of the information contained in a conformal field theory. And there has been proposal by Rui and Takanagi how to compute it holographically, and that also become path-breaking contribution to the community. So people kind of there is a slogan like recently people are trying to understand is space-time in gravity is kind of built out of collections of bits of quantum entanglement, and is there a way to start from this belief or this understanding and then see if we can understand the emergence of space-time from conformal field theory? So that will be the kind of motivation, or to start with, that will be the expectation. So like there is one subject which is called the Tensel Networks, which kind of uses this slogan, or kind of materializes this slogan in a very realizes this interpretation in a very explicit framework. Now I mean, I'm not getting into the details of this Tensor networks or how this kind of came into the picture of ADS CFT research, but in general, tensor networks are like geometrization of quantum states in quantum many-body systems, and there was results by Vidal and then various other people who kind of pointed out that this tensor network diagram looks like a time slice of anti-de-Sitter space. So this variational ansatz for the quantum many-body systems, if we do it for particular kind of tensor networks. So there are several kinds of tensor networks. I mean, what we are looking at is the MERA, which is multi-scale entanglement renormalization ansatz, which works fine for critical systems, so to say, and the logarithmic scale of the entanglement that comes out very nicely in this whole setup. Is there any question?
No.
Yeah. Okay. So I mean, we will not use the tensor networks, so to say, or MERA, so to say, but effectively we will learn something from the MERA research directions, and at some point we may kind of pretend that we don't know MERA, but what we did is like some kind of a magic. We put it out of our hat, and but really speaking, I mean, we learned what we knew from the MERA side, and then we tried to implement in our approach. So that's a starting point, so to say, in terms of more practical words. And so this works for CFT ground states, and there is recent relations between ADS CFT and Tensor network. But this is kind of qualitatively works, but there are several doubts. Also, the evidences are like this is a real space RD structure of MERA, and this extra direction emergence can be seen in a toy model. This entanglement bound in MERA, it saturates and it coincides with the holographic entanglement entropy. Those are the excitements to look at MERA. But there are several doubts also, like, is it possible to explore locality beyond the ATS scale? So why is there a saturation of entanglement entropy? I mean, why is it just a bound in the MERA and it saturates for the holographic case? Can we really conformal symmetry? And ultimately, it's like a lattice formulation. So it will be better to go beyond this lattice formulation and do something in a more continuum sense. So we kind of propose an alternative method where we use this optimization of Euclidean path integrals for ground state wave function in CFTs, but we kind of do the same thing that this MERA network and related research does, in a sense. So to make understand what is this optimization of Euclidean path integral. So here I'm writing the ground state wave function of a conformal field theory in a path integral way. So the ground state wave function is a functional of the boundary value of the fields in the CFT. Now I have a measure which kinds of sits in the path integral. So this var phi is kind of the fields in the CFT, and I have an action, CFT action, e to the minus s, and then there is a boundary condition which says like which imposes this boundary condition. A delta function imposes this boundary condition that the value of the field at the UV, which is z equals to epsilon, is some phi tilde, and the ground state wave function is a function null of that boundary value. So it will be more clear maybe if we see in this picture. So this picture is what is called this tensor network renormalization, which is taken from this paper. And here basically what we do is like we take this path integral and put it on a lattice, which is this 4 diagrams and top left corner, and then we do this optimization where effectively we come to a mera, this bottom left diagram. So this tensor network renormalization is an algorithm which kind of does this very effectively. Now we will look at this tensor. So this is the optimization part, but not in our language yet, in the tensor network language. So tensor network, there is a tensor network renormalization or optimization where we can see it, but we will understand it in our terms, what we mean by this optimization. So effectively what we are trying to do is like this. So we have this space which is spanned by x and z. Z is like this Euclidean time, but we will work in this Euclidean picture where, so for us this x and z will be a space on which we are putting this path integral. So any field, this var phi is a function of these two variables, x and z. And then we kind of start from this square lattice, which is a flat lattice, and then this mera tensor network renormalization does something where we end up in a mera circuit. Like, so basically saying that this mera is reproduced by a hyperbolic space or time slice of ADS3.
So Nilay, do you have like a more concrete connection with Mera in mind, or at this level it's basically structural?
Yeah, it's just structural. So we don't use anything beyond this structural, but we kind of see that there is an algorithm which gives us this starts from this through this tensor network renormalization. We start from, for example, this square lattice, which computes the path integral for me, ground state wave function, and takes me to a mera slice, which is a hyperbolic slice. So we learn this here, and we try to come up with a proposal or some proposal in the continuum field theory so that this can be mimicked in a sense. So it's just structural understanding as of now.
Okay. Thank you.
So basically, so this tau is basically my z, tau is minus z, so to say. So in a ground state wave function, so this is my ground state wave function, and I'm doing this on this square lattice. This tau goes from minus infinity to 0. In the language of z, the z is the minus tau, so it will go from 0 to infinity, and x is my space coordinates, the space coordinate. And then somehow this path integral, when we look at it, this high momentum modes meaning like this is the property of this path integral, then that whatever boundary condition I start from here, it gets washed away, and this is kind of comes out as a just depends on this slice, this tau equals to 0 slice. So if I look at in the momentum space, the momentum modes, high momentum modes around this places is not kind of needed. We can kind of get rid of them. So this is what tensor network renormalization actually does, so that we eventually come to this picture. And it can be seen if we kind of, so there was an attempt to take the mera and make it continuous, which is called the C mera, but it worked only for the free field. But if we just look into the free field case, we can see this ground state wave function, which is written like this, is kind of proportional to the on cell action if we use in a saddle point approximation. And if you use a momentum space basis for the variable phi, this on selection becomes this. Now this factor in the box, it kind of works as a weight factor, and from here we can see like not like this modes which satisfy, which are just below this cutoff 1 over z thing, they only contribute dominantly in the. So this is the idea that I was saying here, that not all the modes here are important. So the optimization basically throws this away in a consistent way. So there was an attempt to use a position dependent cutoff. So basically what I'm doing is I'm starting with this square lattice, and I can use some position dependent cutoff which comes from this, and I can land here. Now this was the attempt in the C-Mera approach, but it was limited to the free field case. But what we learn here is that in the language of tensor networks, eliminating extra tensors in the tensor network is at work for this is optimization of tensor network, which I didn't get into the details. And for free fields, it becomes introducing momentum dependent cutoff. Now the first key insight that we use is this rearrangement of this lattice structure for the tensors in the tensor network. It can be engineered by changing the background metric in the Euclidean path integral. What I'm basically doing in a lattice formulation is kind of changing the background metric on which the path integral is done, but keeping the UV, which is at z equals to epsilon, unchanged, because this is a preparation of the quantum state, and I don't want my final quantum state to be different from the ground state that I am looking at. So with this boundary condition, it's basically changing the metric. That's first insight. But now we are still lacking something, which is what is the counterpart of the optimization algorithm in the
Sorry, I still have a question about this key insight part. So do you understand what's the relation between Hilbert space on one Euclidean time slice to the Hilbert space on another Euclidean time slice in the space-time that is not flat? So say hyperbolic disk, right? You can pick like this Euclidean time slices on this hyperbolic disk, and you're gonna have a Hilbert space on one and a Hilbert space on another slice, right? These slices are not the same slices, right? Because the space-time is curved, right? So there's like not fair relation between these slices. So yes. Do you understand like what's happening with the Hilbert space?
No. We didn't look at that. So that's what I'm saying. It was just the structural lessons that we learned from the tensor network, that it's basically changing the metric. That's kind of first thing that we learned. And then we have to come up with some optimization. What is the optimization? That we have to tell someone that do this thing so that you get it optimized. So that we still don't know. And there is this.
There's one more question. Sorry, but thanks for answering mine.
Yeah, maybe even more general, the Hilbert space in the flat space-time, and then on the hyperbolic space where the Mera lives, those are also totally different, or are they somehow related? Or?
I mean, what I think we didn't look into it, but I think if there is some concern, then this fact that we want to keep the boundary condition fixed here. Yeah. And the state that is prepared, that is fixed, is kind of guarantees us that possibly. But I'm not sure. I'm not sure. If I'm addressing the issue that you're raising, that if it's a curved space and there should be some understanding of the state space, or what you were calling the Hilbert space. No, that we didn't look, but we were happy with the fact that we will impose the state that I'm preparing here is fixed once and for all, and whatever I am doing here should be the most efficient one in that sense. Yeah, we didn't look into so even if there is some attempt to, I think, address the question that both Michał and you were raising. It should be some kind of a boundary effect in that, because I should not worry about any state here. I mean, whatever I do here, change the metric, if that asymptotically here is the same thing, it should be just a boundary effect if someone sets up or like starts looking into the fact that what will happen to the Hilbert space because of the change of the metric. I think even the metric, when I'm saying that the metric is getting changed effectively, I'm demanding that the metric here would be like the flat space, asymptotically.
Sure. Okay, let's move on.
Yeah. Yeah. So now we should think what is this algorithm in our language, and there it gets connected to this recent interest in complexity through holography and all. That is one of the very interesting topic of research these days. So how to define complexity of a state in a conformal field theory? And I know like I won't get into more detail because you are like you have the expert in that section, and I kind of try to learn your recent papers and all. But in our work, we just take it in a very simplistic attitude that we take a reference state, and it's some kind of a unitary operation, some gate operations, and that prepare my state. So it somehow counts the number of gate, which is the as a complexity or computational complexity associated with the state psi that is prepared from this reference state. So our definition, or whenever I will say something about complexity, will kind of attach to this simplistic attitude of complexity. Sorry, yeah. So, but in the literature, there are like through holography several several proposals, as I was saying, to compute this complexity. Now, what we would like to say is that we are also computing some kind of a complexity, which we have given a name, which is path integral complexity, and it is a CFT analog, so to say. I mean, people are trying to come up with a definition of a complexity in conformal field theory, but even though we have not like entered into the details of the complexity and the details in the quantum information point of view, we would say that, I mean, this is some proposal or maybe one candidate complexity thing in the conformal field theory. So this was our key insight, first thing. And now the second key insight is to this optimization. What it means in our language is to minimize this complexity, or whatever we are calling, with respect to the background metric. So I told you that we are understanding this optimization as change of metric. Then there should be some principle which will tell me what that change will be, or when is it most efficient to get a metric. That will be decided by minimizing this. This is the principle that we will use somehow, which in the Tensel Network case was kind of minimizing the variational principle with energy, and that kind of, we are kind of just mimicking the steps in our language. And now, do we have a good, the final thing that we should know is, do we have a good answer for how to define the path integral complexity given one CFT? Now, we are saying that we will have something like this path integral complexity, and we will minimize it and get the metric, the optimized metric. But what is the definition of this in a given CFT? Now, we can only have a good answer in a 2D CFT, because once we understand that this is just changing the metric from this square thing to whatever is the metric after optimization, let us just focus on 2D Euclidean space, and then we use this fact that the only degrees of freedom associated with a 2D metric is a conformal factor to a flat metric. So if I have to minimize or optimize over all possible metrics, it will be in this language figuring out this e to the 2 phi, and it will be minimizing with respect to phi and all. And the boundary condition is such that at like z goes to epsilon, the metric reduces to this. So we will minimize with respect to this phi such that this e to the phi goes to 1 over epsilon. This is our boundary condition, just to maintain the fact that the same quantum state is produced after the optimization. Now, in a 2D, now we look into the ground state wave function. So let's say we are in between the optimization procedure. So generally, my ground state wave function will depend on a metric, which is this G, which is basically e to the 2 phi times a flat metric. Now I will see, this is the definition of the ground state wave function. And you will see that this ground state wave function is just proportional to the ground state wave function if it was a flat space. It just gets a numerical proportionality factor. And why is that? Because so this is the unoptimized wave function, which we started with on the flat lattice, if we say, and this is the optimized wave function. Now this is our proposal for the complexity or path integral complexity, and our proposal is to minimize this factor. Now this is now in more clear terms. Mean is that we need to minimize this factor with respect to phi, keeping this boundary condition. Now, what is this? This is just Liouville action, because in this ground state wave function, this is a CFT action, so this is invariant under the while scaling. We are just doing a while scaling of the metric, so this is invariant. It will not contribute anything, and the contribution will come only from the measure factor. And in a 2D CFT, we know from the calculation of while anomaly and all, the contribution is just a Liouville action. So basically, we are looking at a Liouville action for this 2D CFT case, and whatever we need to do is to minimize or optimize this wave function. Now we take this optimized wave function proportional to unoptimized one through this proportionality factor, and if you look at the Liouville action, it comes with this. So this is the kinetic term, and this is the Liouville potential, and now we have to minimize it. So we can arrange it in terms of whole squares, and from there we'll see that minimization condition actually gives us e to the 2 phi is 1 over z square, so that this is the metric, and the boundary condition is satisfied because z goes to 0 or 1 over epsilon. This is the flat space with 1 over epsilon, obvious thing, and this is the time slice of ADS3. So or hyperbolic space. So what we're saying is that what we started with, we learned from the Tencel Network people that they're doing this optimization and coming to a Mera network, which is a time slice of hyperbolic plane. I mean, we can forget all that story and we say, oh, you do this, start with a CFT, write it in terms of this while metric, and look at the Liouville action, and just minimize it in terms of this, and you will get the hyperbolic plane. So this is some proposal completely in a continuum space and continuum thing. That's the only thing, if at all, improvement over the Mera story. And recently there has been a work by Bartek Czech where with this Liouville action. So I mean, we know in the Mera we have two kinds of tensors. So this is these isometries and this unitary. So he gave an argument where these kinetic terms are proportional to the number of isometries, and this Liouville potential is somehow counting the number of unitaries. And we have generalized it to, for example, like entanglement entropy, one-dimensional system where like SYK kind of Schwarzian action comes out, this excited states into the CFTs and the perturbed CFTs. So like this thermal double state also, this is just doing the same thing. You take 2 CFT and write down the ground state wave function, and then just again minimize this Liouville action, and you get the Einstein-Rosen breeze, or the kind of slice of BTG black hole, time slice of BTG black hole. So this was the content of the first 2 paper. Now, I mean, one can ask me. I mean, you can ask me. This is 2D CFT, and any metric can be written in as a conformal factor to flat space. So relaxation. So what is the counterpart in the higher dimension? I mean, we don't have a very good answer. But if we just follow the thing that, okay, even if in higher D we write it in terms of this, and there is some generalization possible, but this is this is all assuming that, I mean, the metric can be written like this, but this is not always true. But we can come up with what is this value of, or how does this behave with the, I mean, essentially evaluating this is the evaluation of the complexity or whatever for the minimized value of the field and all. And they all show similar behavior with respect to length and all.
So in the context of 3 plus 1 dimensional theory, do you reproduce the anomaly?
3 plus 1 dimensional theory. Yeah. So what you have to consider, actually, even for one, like 1D or sorry, you're saying, yeah. So this is 2D. This is 2D, where this is basically Liouville action is actually the anomaly of the stress tensor, trace of the stress tensor. So
Yeah, sure. Yeah.
similarly, if we go to 3+1D, which you were saying, I mean, you actually you can actually ask for an action which will give you those. I mean, I'm telling about this Riegert action, which actually gives you those anomaly thing. And then you can consider, oh, this is my proposal for the complexity action or whatever, and minimize this. We did that. I mean, we don't have a good principle. If we just look at the Liouville action and try to generalize it to higher D, we get something like this, and from there it follows. But as you said, to produce the anomaly, you need to have this Riegert action, 1/box thing, and so it's not exactly matches with anything, because really you can always write it as a while for.
Okay, thanks.
And if you take the Riegert action and just go ahead and minimize it, then you get actually hyperbolic slice, or I would say H3 as a solution of that. But that is not actually the minimized thing. It kind of extremizes it, but the action is unbounded from below. So there are some technical difficulties if we start with the Riegert action, and so it's not very well understood in the higher D thing. So yeah, so now I was asked to look into the third part of the or the second half of my talk would be to look more carefully into the third paper, which we kind of extended these things to part of CFTs, or like but can we extend these ideas to the CFTs with relevant perturbations. So I will be a little more detail in this part, little in the sense, like I'll try to walk you through the calculation a little bit with the basic understanding. So what we do here is like extend this path integral analysis of holographic emergent space to non-conformal examples. In particular, we are kind of when we say we are perturbing it, we have something in mind of this form, where we take some primary operator and deform the CFT action, and we would like to see, can we generalize our optimization procedure to these examples. Now, I mean, we will also consider this fact that we would like to keep the ground state wave function for a perturbed CFT proportional to that in a flat metric. By which I mean, like just in the sense of preparing the quantum state at the boundary condition, we would like to have that the wave function is proportional to the unoptimized thing. But here we cannot clearly do it more generally. So what we have to do is we have to take this coupling lambda depending on the position. So this is some position dependent coupling constant will be introduced. And this position dependent coupling constant in a natural sense should be identified with some bulk field in the ADS space. And this generalized path integral complexity actions for this perturbed CFT will now depend actually on the metric and as well as on the couplings. So I will be more careful, but these are the highlighting points of the thing that I'm going to say. And finally, the metric after optimization should correspond to some perturbation of the hyperbolic space metric as expected from the ADS CFT. So these things I will explain in what I'm going to say right now. So what is the basic principle? So now I've told you that the wave function should now also care about the coupling, which gets into the story through this action, which is not just a CFT action right now. We have this fact here, and to start with, we would like to evaluate it on a flat space metric, which is like this. This is the picture that when I showed you the first part. This is the square box picture where before the optimization. So this is a flat space with this fact that each box of unit area has one lattice in that sense, that kind of understanding. And then for the optimization procedure, what we should do, as I told you, is to introduce position dependent coupling, and then we will again use these boundary conditions, because we want to keep the quantum state that's prepared that to be the same. So by which I mean, what I mean is that when I take z or z going to epsilon, they should come down to these constants, z naught and lambda naught. Constant in the sense they can be x dependent, but this boundary condition should be maintained in the optimization thing. And if you see here, g naught and lambda naught are the flat space thing, or before the optimization when we started. Now in general, the wave function should be something like this, and there is no way to expect that it will be proportional to the unoptimized wave function, because now it has a non-trivial lambda dependence here. But the approach that we would like to take is that if we demand this, that the optimized wave function will be proportional to the wave function before the optimization, and just proportional meaning there will be again some numerical factor here which we should optimize. That should actually fix this phi dependence of the lambda. Yeah. So more specifically, we would like to have the wave function after optimization, which now depends on both the metric and the coupling constant, to be proportional to the unoptimized metric, which is here, unoptimized wave function, which is here, and with some proportionality factor. And the optimization will again be minimizing this, or this, and then that we will say something like complexity for this case. Now, what is the justification that this way of demanding that the wave function is proportional, which in turn fixes this lambda, is that we will see what happens in the ADS story. I mean, in the ADS story, we know how to perturb it with a bulk scalar field and backreacting it, and we have a way to compare these two. So that will be the justification of this naive expectation over here, and which I will come to at the end. So intuitively, what we are doing is like, if we look at so here I'm looking at the partition function. So this is kind of a double copy. So think of this like being cut here in the middle, and from here down this way I have one copy, and starting from here down upwards I have another copy. So this is some kind of mod psi square, and which computes the partition function, or the capital Z for me, and the operators which are like kind of the perturbations which are kind of inserted over here. And then we will again do the optimization such that possibly the mirror network or the hyperbolic slice will come up with some perturbations, with some change in the metric over here, and that we have to compare with the ADS or the bulk expectations. So just to going back to the conformal case, that means I'm considering lambda equals to 0. I mean, there is another support or another way of understanding that this expectation of the wave function being proportional to the unoptimized one after the optimization, that can be seen from this slide, is that just from CFT arguments, I know how operators should scale under a while scaling by this factor phi. So this e to the phi is my while scaling from let's say, and then this is just from CFT point of view, that if I have a endpoint function on like metric to phi and to phi naught, then due to this while scaling, they just change by this factor. Now, so this here I'm using this is kind of, if you want to say the definition of this endpoint function, that this I will insert these operators weighted with this mod psi square and do the kind of path integral in a double copy sense, which I explained in the previous slide. But we need to keep this boundary condition that if I say that this is the metric and phi should be optimized, then this e to the phi at z going to infinity, z going to epsilon, sorry, there's a typo, this z should be here, epsilon should be 1 over epsilon or e to the phi naught, which will give me the flat thing. And the fact that if you look at here, that z going to epsilon phi of this thing, because of this relation, becomes e to the phi naught. So this thing actually vanishes, or this whole numerical factor becomes 1. So the endpoint function or the correlation functions, they are invariant under this optimization or whatever we are doing. But if this has to be this correlation function has to be same before and after the optimization, then the wave function is proportional to a numerical factor. It cannot be anything other than that. So this is also one way of understanding, which we realized when we were doing this part of CFT case, that in the first part, when I told you that the wave function is expected to be proportional, comes from this understanding. Now, going back to the part of the case, so what we are trying to see is that we will look at some wave function, and this will be proportional to some factor, which will have informations about this lambda, and just numerical factor times the unoptimized wave function, which is here. And this also comes from the fact that at z going to epsilon, on that slice, the correlation function after optimization should be same as the correlation functions on that same slice, z equals to epsilon, before optimization. Now, this whole thing has a RG flow kind of interpretation, which is kind of a general explanation supporting supporting what we are trying to say. And the key idea here is this fact that we want to keep the same quantum state even if we while rescale the metric. I mean, at z going to epsilon, and that means we are locally changing the coupling constants. So this is basically what we know by this RG flow equations. So lambda are my coupling constants, capital lambda is some cutoff. This is the definition of the beta function, and this is how this is the Kalan-Zimanzik equation, or the partition function being acted by this operators, and zeta considers contributions if I have from, let's say, anomaly or anything. So this is one way of understanding that the physics is same when I'm doing some scale transformations. Here also I'm trying to keep the quantum state invariant, and I'm trying to decimate the tensors in the tensor network language, or I'm optimizing the metric in our language. So the regularization in our case can be thought of like this, because the metric is like this. The optimization is done over phi, and then the unit cell is kind of determined by this e to the minus phi, such that one unit area box in this metric reproduces one tensor. So this is one natural way of regularizing this thing in our case. And we should also remember that the fine-grained lattice that we started with, or on the square lattice, there also, like we had this, and this thing should reduce to these two things when we kind of take this z going to epsilon or the UV thing. Now in our case, what we should do is, like, this e to the phi should be understood as some cutoff, capital lambda, which were here like appearing in this RG equations. And now if we consider e to the phi, which is the while factor, is some kind of an cutoff in a way, then the RG equations kind of translates to this thing. And here I'm using the general beta function for some coupling, which is determined by the dimension of the operator. Now,
so Nilay, so is the statement correct that when you do these calculations, it's as if you're keeping the proper cutoff fixed, the proper length cutoff fixed?
Yes. Yes. We are trying to understand.
And do you know if in the quantum field theory literature in curved space, like, this is something that people do on a daily basis, or that's unusual, or do you have a statement on this?
I have to think about it in a way. But Yeah, but like we have to do something more than that because of this position dependence and all. But the basic idea is to understanding this whole lambda flow is lambda flow in the sense what I'm saying is this change of lambda because of this e to the phi. Because if you so what I'm trying to say is if you make e to the phi, this phi to be large, it's kind of going to the UV, and phi, or I'm confused. Phi large is going to, yes, phi large is kind of going to UV, and phi small is going to the IR. So that way we are just kind of using it, but in a more quantum field theory sense, I have to think about it. I cannot come up with something readily.
Okay, sure. Let's move on.
Yeah, but here we have to do some more, which is kind of this position dependence in the sense that like we are doing this thing locally. This lambda is depending on these functions x and z. So this is some kind of just generalizing this thing here, and now we can more generally solve this in a perturbative sense, in a perturbation series on lambda naught. Just like which will be this, such that the boundary condition is satisfied, and then one can look at the Kalanzi-Manzig equation here. So here actually this is some typo here. What I'm considering is I'm including partial derivative sense. I should be using some d maybe. So this equation, and this can be most generally solved like this. Now I mean, one can check that if one uses this lambda phi with keeping in mind that this is the boundary condition, then the general wave function which was like this, and where it was not sure whether it would be proportional to the unoptimized wave function, it actually comes out through this, that you can write it like this.
So can you remind us what is psi? Sorry.
Psi is the ground state wave function. This psi is the ground state wave function.
Oh, psi. Yeah. So the last term in the Kalanzi-Manzig equation.
No. Here.
Yeah. What's this?
This is this anomaly contribution. So if you want to know, if you are doing, for example, lambda equals to 0, conformal class, this will be the Liouville action or
okay. Okay, good. Yeah, thanks.
Yeah. So then from there you can actually generally, this is a most like a formal solution, but in a perturbative sense, one can check that like this basically becomes this. So this is one justification from this RG flow or this kind of interpretation. And then I mean, what we can do is like we can just evaluate this normalization factor, what it becomes, and you can in a perturbation series, and you can see that this is when lambda equals to 0. This is the Liouville action. Then you have a 1-point contribution, then you have a 2-point contribution, and then higher orders. This 1-point contribution is because of this 1-point function of the operator, and 2-point function is this n2 point is because of the 2-point second order in the perturbation series. And then in some more detail, if we look into the 1-point thing, can
we go back to the previous transparency, please? So do you have this formula for n that you derived before coming from the Kalanzi-Manzig equation? It's valid to all orders in lambda, or is just valid to quadratic or linear order in lambda?
No, we believe it's valid to all order in lambda.
Okay, so in principle, can you iterate it to all order, like this equation on this transparency for n? Like, do you have like all terms all the way to at all orders of the expansion in lambda?
Yeah, but then you have to know all the correlation functions, higher point functions as well. Yeah, then in principle you can write it down. We are just looking at the perturbation up to this quadratic order.
And this correlation functions are correlations of understood as CFT correlations.
Conformal perturbation theory. Yes. Yes.
Oh, okay. Okay. So
These are evaluated as a CFT, but
Mhm.
then you have a lambda, which is basically, I mean, this is exactly conformal perturbation theory. You compute
Yeah, sure.
it in the CFT, but the interpretation is in the perturbation sense.
Okay.
And this 1-point functions will be important and non-zero because now we have a boundary. So if you have a boundary at z goes to epsilon, then the 1-point function is this. And if you use this here in this in 1 point, which actually comes out to be this. So this is some constant contribution, but we have assumed this delta is between 2 and 1. Then this is a divergent one. So, but you can see that this will not contribute to the optimization because this is phi independent. This phi independent. So this will not contribute to the optimization. But if we want to know what is the complexity answer, this is a divergent contribution, constant divergent contribution to the complexity thing. And similarly, one can compute the 2-point function. And some calculation, you can see that this is actually dependent on phi, where I mean, there also we have a boundary, but you can start with the plane and then use the boundary contributions. The boundary contributions will be such that either one of these 2 points goes to the boundary, which is actually already taken care of in 1-point thing, and then there are other possibility where these two kind of come closer to each other, or they goes to the boundary. And but that will not contribute to the optimization again, because the boundary condition is a constant divergent thing. And so finally you will see that you get a form which is like this complexity function. But this is before minimizing this. Now one have to minimize this, which means like so this is the up to quadratic order. You can see that this is the Liouville action part. This is the 2-point n 2-point contribution, and this is the n 1 point, which is independent of phi. Now, if you do the minimization, you can obtain this in a perturbation series of lambda naught square. And again, I mean, you can expand the these terms using this equation in terms of lambda naught square, and this thing actually in a perturbation series. And you can compute the complexity functional for the minimized values. So once we have minimized here, and we can use this and compute these functions. So there's some range for the delta. Actually, delta is between 1 and 2, which is like the when we go to the ADS case, this will come out as the standard quantization. But we don't understand the alternative quantization or anything. But the standard quantization corresponds to this delta is between 1 and 2, and in this range we get a result. Ultimately, if we carry on the calculation like this, so these are the bulk contributions, and these are the boundary contributions, and this is always dominant. So the dominant contribution to the complexity comes from the 1-point function, and the sign is determined by the constant, and then one has to fix the UV thing and all. But only thing that we can say is we learned, or we see, is that this is some kind of a divergent contribution to the complexity, and it comes from the 1-point function in 1 point here or here. Yeah, so this one. So this is the complexity, or actually this is not the complexity. This is the change in complexity. This is the change in complexity over the conformal one. That is, I'm writing only this part. Now, what is not the justification part with the ADS CFT? So in the ADS CFT sense, what we are considering is a scalar field, massive scalar field in the bulk, which has an action like this, and then according to the standard bulk to boundary relation, the scalar field solution should go something like this. There is a normalizable, non-normalizable mode. One is to the source, other to the expectation value of the observable in the CFT, with this relation of the mass with the conformal dimension of the boundary operator. and one can really write this bulk field in a way such that in this perturbative sense, and then one can look at the linearized back reaction of the scalar field, which is written here like this. And if we consider the linearized Einstein equation, and just for the ADS3 CFT2 case, this action comes out something like this. Now this structure is also same like the overall answer that we had seen here. I mean, the coefficients, the order 1 numbers, they don't clearly match because one has to specify the normalization and everything. But this overall structure, which came out from the minimization of the path integral wave function approach, actually matches with the ADS CFT expectation. And moreover, we can compute in the ADS CFT case the e to the phi, which comes out like this, and this actually matches up to this normalizing, this numerical factor. This I think the denominator matches, but this 2 minus delta is absent. Just see here, yeah, some to delta minus 2 by 2. This might be some detail regarding the how one normalizes the operator and all. And so this actually agrees up to a numerical order 1 factor, which depends on the details of the equalization and normalization of the operator. So just to summarize, in this, at least in the last part, we have so actually we also did some free scalar and free fermion calculation. But for the free massive scalar case, we actually did some similar position dependent mass analysis, but that's not a primary operator, we know. So we used some kind of a Mabuchi action, and we kind of that kind of does not fit in the program that I was, or the analysis that I was presenting. But for the fermion case, the massive fermion, that being a primary operator, that actually satisfies what we were trying to see. Those we have actually calculated in some appendix in our last paper. So basically, we present some evidences how this optimization mechanism works, based on some general arguments of RG flows in the field theories. This optimization is performed by minimizing the path complexity functional, which depends on the metric and also on the relevant couplings for the perturbed CFT case. And we compute this metric perturbatively, find it that it agrees with the time slice of hyperbolic metric perturbed by a scalar field in the CFT correspondence. And we estimated the contributions to the complexity from these relevant perturbations. So thank you, and I'm not sure if some of you are coming to this ISM 2018, which is going to happen possibly next month. And in any way, you are welcome to come to our institute at Kanpur, and possibly one of your previous friend, Diktarko, is also here, and we are trying to build up a study group, and you are most welcome to come to us. Thank you.
Thank you. Thank you.
Any other questions?
Well, I have a few, but maybe some other people have first.
I go from online.
And somebody online?
Microsoft is one.
Yeah. Okay. So maybe then I go ahead. So this agreement that or like partial agreement that you noted, perhaps shouldn't be too surprising, right? Because like both calculations can be phrased as conformal perturbation theory.
Yeah.
I mean, the calculation of the metric in the bulk and the optimization that you're doing.
Yeah.
And the fact that the contributions just differ by normalization is something that doesn't look too surprising to me.
Yes.
Can you comment on this, or you just?
But this fact that just you take this ground state wave function and minimizing that, and from there I get a e to the phi, or the perturbed metric, but the back reaction calculated from that part actually agrees with the ADS CFT expectation, was some kind of a check that yes, what we were trying to say in the first two thing for pure ADS or pure like 2D CFT can be extended to this Porter thing. So this was some kind of a support to the first part that I was saying. I mean, yeah, but maybe I did not understand the.
No, I think that was okay. And the other question is, do you see like some notion of or some remnant of the C theorem at the level of this action? Say suppose that you deform your theory, and flow to another fixed point. Like maybe it's not visible at the level of the calculations you did, right? And this is a CFT, and
no.
you see some features like this in these.
That would be very interesting, but no. Actually, if you just see the first part, we hardly used the fact that this is a holographic state or large C. That actually comes into play when we looked into the deformed case. When we deformed it with the operator, there to match it, we had to use this large C and all this thing. But other than that, I mean, there's a lot more to go, I think, before we address the kind of C theorem and this kind of thing. The first interesting thing is, I mean, this is just a hyperbolic slice. Can we say something about the time component, which will be the total ADS metric or any time-dependent processes? So yeah, but we are far from all that.
And on the latter comment, like, can you please go back to the slide where you were showing the bulk metric when you were comparing? Okay.
Yeah. So this is what is expected from the linearized Einstein equation in the bulk side.
So how do we? Yeah. Okay. Okay. So this E2 defies that you match it to what? You match it to f of y over y squared.
Yeah. So if you start with this metric,
yeah,
which is, and this fy will be the back reaction when you take phi to go like this.
Yeah.
And then do a coordinate transformation from y to z given by this, and that actually takes you to this final.
Okay, good. Okay, thanks.
Yeah.
Thank you.
Okay, there are no more questions. Let's thank Nilay again.